Hello and welcome to this new video where we discuss mathematics and physics on the board. Today what I would like to discuss is simply the basic idea there is behind so-called Christoffel symbols that are heavily used in differential geometry but also in general relativity as well, and to some extent they could be used as well in quantum field theory and so on and so forth. So that's what we are going to do today. Basically look at a very simple example, perhaps a bit too trivial, but where we are going to be able to formulate it by using Christoffel symbols. Okay, so what is the system we are going to look at? Well, we are going to look at the description of a vector, so in particular initially a position vector, in a polar coordinate system. So we are going to start with a Cartesian description, and this Cartesian description here is characterized by this rectangular coordinates x and y, which correspond to this perpendicular axis x and y. And then I'm actually looking here at a position vector that I call r, and basically that's it. So what I can say is that I can look at the projection on the x-axis and y-axis and write that r is equal to x and then ex plus y ey. So that's a traditional thing of Cartesian coordinates and linear algebra, where basically I'm expressing a vector here r with an arrow on top signifying that this is a vector, and then here x is the component of the position vector r relative to the basis vector ex in the Cartesian coordinate system. The hat that I put on it signifies that this is a unit vector, and here plus y ey, where y is the component of the position vector r relative to this particular basis vector ey. Okay, now as you can see on that depiction, ex and ey here are basically some kind of absolute vectors that do not have any specific they don't necessarily they are fixed basically. In whatever we look at, these things are fixed, right? So that's kind of the basic starting point we are going to look at. Now, how do we introduce polar coordinates from there? Well, we can introduce polar coordinates by employing these equations here. So if I introduce the angle theta here between the x-axis and the direction of r, then I can basically express the coordinate x and y in terms of basically the hypotenuse of this right triangle and the corresponding angle here with the cosine or sine depending on the trigonometric formula I'm using. So for example here, if the magnitude of my vector is actually called simply lowercase r, then from basic trigonometry I get that x is equal to r cosine theta and y is equal to r sine theta. So once you have that, what you can do is express the position vector in terms of polar coordinates, but in the Cartesian basis. And so if you do that, you simply substitute the values or the expressions of x and y with these ones. So you're going to get r cosine theta ex and then plus r sine theta ey. Okay, so again, this is a sort of intermediate expression where you express the position vector or whatever vector field you would kind of consider in terms of a new system of coordinates, but still in the old basis. Okay. Now, what you can do and notice here is that you can factorize basically by r here. So you can factorize by r, and actually notice that you can write cosine theta ex, and then plus sine theta ey. Now, this particular object is basically directed along this particular direction, and turns out to be a unit vector, because cosine squared theta plus sine squared theta is going to be equal 1. So what people do in that case is that they call this vector ER, like so, ER. And notice that this one actually is going to depend on theta. Okay? Now, one of the things you can ask is basically say, okay, if I have got this ER, which is actually now in this particular direction, you can ask yourself, and that depends on theta. So you see, as this radial direction is changing, so theta is varying, this ER is going to change. And then the next one you can ask is basically, can I actually find out what happens, or can I find a vector which is perpendicular to this one, and which has a property that basically it is like its cross product is going to be the same as the cross product of x with y, of ex with ey. So you can basically introduce a new vector, and so here I'm going to write it. Basically, you can introduce a vector that you want to be always perpendicular to ER of theta for a given theta value. And so you introduce, and there is a convention to do it, and that's what I mentioned earlier. You need to have the convention that the cross product would have to be the same as that of ex with ey. And then basically there is only one possibility, which is this e theta, that's how it's called usually, that is going also to depend on theta as well, and that's going to be minus sine theta ex, and then plus cosine theta ey. Okay, so that's basically another one that you can introduce, and this is going to be tangent to the circle, if you will, and perpendicular to ER. So here this is E theta. And essentially you've got a vector that goes in the radial direction corresponding to the radius coordinate, and then you've got a vector that goes that is always tangent to a circle you would draw corresponding to the angle theta, and that basically corresponds to a direction alongside theta. Okay, so a sort of angular direction. So basically that's the idea. Now what we can try to look at is basically with these two expressions. So here we've got an expression of ER, and here we've got an expression of E theta. Now what I can say is the following. In general, and that's basically where I'm coming with my definitions of Christoffel symbols, is that in general, if we have a basis, and the basis here I'm going to call it, let's say it's a set of vectors that I'm going to call EI, like so. And then I is going to range over the number of coordinates you have. Maybe I can be replaced by the names of the coordinates, depending on what formalism you want to use. That's not really a big issue here. So in general, if we have a basis EI, that a priori is going to depend itself on the coordinates of the system, that may depend on the coordinates. So you see that here I'm talking about a basis, so a set of basis vectors, basically, that is going to depend on the coordinates themselves of a sort of vector position here. So depend on the coordinates. So that would be, you can view that as vector position or coordinates in more general sense, as if you had essentially, an atlas with which you've got some charts of coordinates to localize a point in the world you're living in. Okay, so you could think of GPS coordinate system, for example, something like this. So depend on the coordinates that I'm going to call here just x, for example, xj, doesn't matter. And again, it can depend on any subset of these coordinates. Then, and then basically this is what we're going to say. If you take a derivative, the derivative of basically one of these coordinate vector, then this derivative is going to lead you to, in principle, it's a linear map, and this linear map is going to, return another vector, and this vector is going to be expressible in the local basis Eij. Okay, and so that's basically what the Christoffel symbols are about. So essentially, this is going to be like so. So you've got that by definition, you've got d of Ei, and then here you differentiate with respect to xj is going to be equal to, and that's a definition, that's equal to the sum over k. So again, k here is going to be running over the coordinates, labels basically, of a set of numbers that I'm calling here gamma, I, j, k. So that's often how these things are described, at least if you look at the kind of baby version of this, and then E, K. Okay, so you see that basically this, that's basically a definition, and this definition is saying something super trivial, and this trivial thing is simply that derivatives are linear maps, and basically they are going to transform whatever basis vector you have into a linear combination of the basis vectors in the kind of original coordinate system. Okay, and so that's kind of the idea. And so these things here are called Christoffel. So these things are called Christoffel symbols. Okay. Now, what I want to do, and that's just basically to clarify things, is just to show you that although this looks kind of very esoteric, actually we can figure out these things fairly easily. And I just want to give two applications. The first one is to find out the Christoffel symbols for basically the Cartesian system of basis, so the Cartesian basis, and then look at the same for the polar basis and see kind of how that goes. So basically, let's look at application. And this is just to show you again that this is actually fairly easy to do. So the first one we are going to look at, and are going to be fairly straightforward, is a Cartesian basis. And so this Cartesian basis, again, is Ex and then Ey. Now, what can we say here? Well, what we know, and that's what I've stated, is that this basis does not depend on the coordinates, okay? On the coordinates. Kind of x, y. Okay? And so consequently, because they don't depend on it, then of course what that means is that you're going to have d of Ei. In that case, d of xj is actually going to be 0. And that's actually for any Ij that is equal to x or y. Okay? okay, here I put ij that is x or y. You need to understand that xj here is going to be y or x, and here the I is going to be x or y. Okay, so I'm basically using here these indices as meaning x or y when this is for E, and for the coordinates that directly x or y. Okay, so basically here the only possibility is that because you need to have 0 for any I, j, etc., is that you need to conclude from it that gamma for the Cartesian system is going to be equal to 0, okay, for all possible values. So that's fairly easy, you see. You actually, without knowing it, you were already aware of a set of values for Cartesian. Right, so what we are going to do now is we are going to do it on that side, so for polar coordinates now. Okay, so basically we've got the in polar coordinates. What we can do is that we know that there is ER, which is equal to cosine theta EX plus sine theta EY. And so what we have as well is that E theta is equal to minus sine theta EX, and then plus cosine theta EY. So what we can do basically here is differentiate. So first of all, one of the things I know is that if I try to look at d of ER, dr, because that's a polar coordinate, what I'm going to find is that this is the same as d of E theta dr. That's actually equal to 0. Okay, so that's the first thing I can say, because you see that the dependence in the coordinates is only in theta. Okay, it only depends on theta. There is no dependence in r, at least in this polar basis. And these vectors here, Ex and Ey, we've already said are constant. Okay, they're constant or uniform or whatever, but they don't depend on coordinates. So basically here what I have is that dEr dr is equal to 0. So what does that mean? Well, that means that if I replace over there, I'm going to have d of whatever here I, again in the polar basis, and then here I'm going to put dr is equal to the sum, and then over k, and k here is going to take the value theta or r, and then of gamma, which is here we have r, and then I, and then k, and basically I should not forget ek, and this is going to be equal to 0. So the only possibility for this to be equal to 0 is actually for these numbers to be 0. Okay, and the reason why is because this is a basis, so they need to be linearly independent. So it's not like you can compensate kind of one with the other and so on. Okay, so the only possibility here is actually to get that basically gamma Ri and then k is equal to 0, and that's actually for any I and for any k. So that's the first thing we have, that these numbers are actually 0 if I put r as an index here. So that's the first one. And then one of the things we can look at is when we actually take derivatives. So if I actually look at d of ER and then d theta, you can realize that the derivative of cosine theta, so you know that the derivative of a sum is a sum of the derivative, so derivative of cosine is minus sine theta, derivative of sine is actually cosine. So it turns out that d of ER d theta is equal to E theta. And as it turns out as well, we have that d of e theta, if you do the calculation, d theta is actually equal to minus er. Now, correspondingly, if you then replace that by a sum like that, then what you're going to find is the following. You're going to find that gamma, and we need to be a bit careful, so that gamma, theta, and then r here, we need to be okay like this. So gamma, theta, r, and then here that's theta is equal to plus 1. Then we have that gamma, we've got theta, theta, r is equal to minus 1. And all the other terms are 0. Okay? So that's basically the, like the bottom line is that the other ones are going to be 0. These are the only ones that are non-zero. Okay? And so what happens is that basically with this particular table of numbers, plus 1, minus 1, and everything else is 0, essentially you can basically find out all possible, let's say, calculation involving derivatives of these basis vectors in the so-called local basis that the polar coordinate system is representing. Okay, and in some future videos we are going to look at basically how do we apply that again in a simple to a simple problem, which is that of retrieving the formulas for velocity and acceleration in mechanics. So basically that's the idea. If you've got any questions or comments, by all means do let me know, and otherwise see you in the next video.